In dynamic surface reconstruction, noisy and outlier-driven data poses a difficult challenge for maintaining both good performance and good output quality. Current online methods perform an L2-based reconstruction, reducing noise by smoothing. In contrast, robust L1 methods produce much better results but are too slow for interactive applications. For example, the weighted locally optimal projection operator performs an iterative L1 minimization of resampled particle positions based on discrete attracting forces defined by the point cloud. In our paper, we present a novel, continuous formulation of this LOP operator, which allows us to significantly speed up the reconstruction without sustaining a loss in quality. A hierarchical expectation maximization is applied on the input points to quickly compute a Gaussian mixture representing their density with only a few Gaussian components. Here we see this density as well as the individual Gaussian components of the mixture. Our continuous reformulation of this LOP operator can now be applied to this reduced mixture instead of to the large original point set. Due to the reduced computational load, this continuous method is up to 7 times faster than discrete LOP algorithms. By applying a regularization on the mixture computation, the density preserves features and is able to distinctively model outlier points. Here we see the iterative fitting process governed by the attracting forces of the density exerted on the particles. A sufficient convergence can mostly be observed after around 10 iterations. Occasionally appearing density points or rods indicate tiny Gaussians modeling the energy of only 1 or 2 outlier points. We see that the reconstructed surface robustly follows the actual surface signal of the input data. Like weighted LOP, our method also elegantly incorporates proper energy balancing in datasets of varying point density, as given in the horizontal density patterns of this phase. The left side shows the original density, where denser regions would lead to higher particle concentrations. By applying density-based weights to the mixture, we can however obtain a more balanced energy distribution, achieving a more uniform sampling. Our method faithfully reconstructs difficult objects with thin features and a large amount of noise, while being several times faster than a comparable GPU implementation of weighted LOP. We use an efficient output-sensitive implementation which can perform the entire algorithm in screen space after projecting the visible part of a model to the screen. Here we see a large gargoyle of over 300,000 points, where approximately 60% of its data is used for screen space reconstruction. Error measurements against the ground truth surface show that our continuous formulation achieves a comparably higher reconstruction accuracy. Furthermore, it allows for using much more particles than there are points in the model, which is known to be problematic for previous LOP variants. This makes our method applicable for robust point cloud upsampling. People get regularly annoyed when they try to scan small green boxes, but the scanner exhibits too much noise for a decent rendering. Applying L2-based reconstruction methods typically results in smoothing artifacts, which is especially apparent at sharp corners. We show how to extend our continuous formulation from before to be applicable to a continuous representation of the object's normal field. This allows for a robust local reconstruction of splat normals at sharp features. Here, a similar comparison on a more complex tabletop scene.